Hello everyone, my name is Emmanuel Hernandez. I am a robotics engineer that just graduated from college last year. And this is the first time that I've been involved in a data science project. So I'm very excited to present to all of you the things that we worked on as a team.
We are a team with many different skills, views, and good problems, like yours. Today, we want to share how we developed a solution for forecasting a drug inventory. And so, by the busy Chilpancingo metro station in the heart of Roma, Mexico City, we arrive at the Dalinde hospital. But first, let's take a look at how we got there, shall we?
We first got together in WeWork.
We never met each other. We were complete strangers.
To develop a case to solve a problem in Mexico City.
It was a random chance because other teams were prepared because they were working together in their own companies.
In 2019, the hospital reported an increase of 30% on the cost of the drugs that reported a shortage. This was because they had to go to buy the drugs to different drugstores rather than from their original suppliers. We got commitment and cooperation from Ivan Ramos, who is the Dalinde's hospital controller, and from Julio Perez, who is the head of the pharmacy. They gave us data on monthly amount demanded of patent drugs, daily amount purchased of patent drugs, and the daily amount of purchasing orders that were not fulfilled. From the 1,681 time series, we wanted to analyze first the ones that were missing the most and that had the most monetary value. Then we encountered the fact that not all of them had continuous data. So we got only the ones that were continuously consumed and bought during our 24 months time period that we were training our data on. We got only 87 patent drugs from that represented 83% of the total cost from the 24 months, which was very good for us. Our universe of 87 patent drugs adds up to 4.4 million pesos, $226,000. From those 87 patent drugs, we discovered that 9 were missing, and those 9 represent 40% of those drugs, which means that these 9 that we're gonna focus from now on represent 1.7 million pesos, $91,000.
In parallel, during the EABA, we translate our work to the cloud. We use an EC2 Ubuntu image in AWS, and we create a network security group.
And we expose some ports from this EC2 machine to the internet.
We recreated the environment and built different containers in a Docker system with Portainer.io, 2 development machines with Jupyter, 1 database with PostgreSQL, and 1 internet site with Django.
From those drugs, we did a lot of things. We did 2 scrapers. First of all, to complete the database
with market data and uses of medicines in the human system to get organ systems that medicines are supposed to treat.
This dashboard can look at historical data of the top 9 drugs and give the user business intelligence capabilities like see shortages over time, also do a search by purchase order, med code. You can also appreciate an error comparison between models and by month. And you can look at a specific medicine and the suggested amount to buy that the models and the process controller suggest.
The hospital lacks of a prediction model that can help them to plan budget in advance. So we created 2 prediction consumption models based on our time series that we already selected, and we also created an PID controller for logistical usage for their inventory. An ARIMA is an Autoregressive Integrated Moving Average statistical process that works with time series, and it's very popular to forecast economic variables such as supply, demand, and GDP. It fits very well to our problem because we do have the demand for patent drugs and time series. So ARIMA is a well fit for us. Because not all time series have the same structure, we had to learn the parameters for each of our 9 time series following this methodology. 1. We performed a Dickey-Fuller test of unit root to check if the time series was stationary. 2. We plot the partial autocorrelation function to verify the autoregressive parameter and suggest an order for it. 3. We plot the autocorrelation function to verify the moving average parameter and suggest an order for it. 4. We estimated the ARIMA model with the parameters suggested from our observations of the Dickey-Fuller test, the partial autocorrelation function, and the autocorrelation function. 5. We recalculate the ARIMA with different values of the parameters and compare the ARIMAs using the Akaike information criteria. 6. We select the ARIMA model with the lowest Akaike information criteria for each of the 9 time series. With this methodology, we got our results and estimated parameters in order to make our forecasts.
This model is well suited for predicting sequential data, such as time series, due to a loop that is implemented in the layer architecture, enabling it to remember previous data. The long short-term memory recurrent neural network has the capacity of weighting data with antiquity, balancing these attributes and their importance for prediction. This model was fitted using only medicines with complete data, and their attributes were normalized before fitting them into the model to ensure better accuracy. A validation split was used when training the model to monitor its performance and prevent overfitting. Finally, the performance of our model was measured for our top 9 drugs, which comprised the test data split. We found that, on average, the model is able to predict the demand 1 month ahead, with an error of 4 boxes of a medicine. And this error increases to 17 boxes when trying to predict 3 months ahead.
When we compare the performance of our models using the mean absolute error metric, we can see that our baseline model doesn't perform very good. But the ARIMA and the Recurrent Neural Network work very good. In fact, the ARIMA works the best for 3 of the time series, and the Recurrent Neural Network works the best for 6 of our 9 time series.
A really cool part of the solution we built is a process controller to go back a normal inventory level when facing events of demand. The PID controller is a mathematical equation that simulates the system behavior by calculating 3 constants: proportional, integral, and differential. We ran 2 exercises that confirmed that the current methodology is not sufficient enough to fight assortation. We also ran a linear regression of the variables, amount received and amount in inventory, and discovered 6 slopes close to 0 and 3 negative slopes, demonstrating that the inventory levels always have shortages on average. In this process diagram for a lasso control closed loop, we can appreciate how set point, or decided inventory level, and PV, or current level, go in a model for processing, and after some iterations, we reach the decided output level recommendation.
Our business case was built from scratch. It's hard to predict more than 1 step ahead when working with this time series. It is a living thing. We began with uncertainty, but now we are sure of the goodness of data science and machine learning tools. With our solution, we estimated 4.48% of savings on the total cost from the forecasted drugs. This analysis can be reproduced with other drugs and commodities, not only for one hospital, but for the health systems of Mexico City, Latin America, and the entire world, guiding budget decisions and providing health security for our societies.